Hello and welcome to another LeetCode video. Today we're going to be doing the problem of the week for this week, and it's check if the number is a majority element of a sorted array. It's a pretty straightforward problem, so it's just saying given a sorted nums array, return return a target if the majority, or it's even easier, return true if the target is a majority element or false if otherwise. A majority element in an array is an element that appears more than nums lengths over 2 in an array. And so, since you're actually given a target, it would be quite easy to get a target as well, because the target, in order for it to be the biggest element in the array, would have to be at, like, if it's sorted, would have to be in the middle. So you can just check for the middle element in an array, right? But either way, you're given the target. And so, how are some ways we could do this? So a really easy way would just be like if you have 2, 4, 5, 5, 5, let's say, right? 6. And a really easy way is to just take the count of the number. And so anytime you just have some count variable, right? Like count equals 0. You just go through it one by one by one by one, and you just, if it's whatever number you want, you add one to the count. And so this would be 3. And then you just say, okay, the length of the array is 6. So I need the count to be greater than 6 over 2, right? And so 6 over 2 would be 3. And you'd say, okay, well, clearly it's not equal to, it's not greater than, right? It's not greater than 3, so then false, and so on. So that would be a linear solution. That would be pretty straightforward. Let's see if we can improve this. So how can we take advantage, once again, of the fact that it's sorted? So we could improve it a little bit by, like I said, if the array is sorted, then the number has to be in the middle, right? So if it's, like, let's say it's 2, 4, 5, 5, 5. And there are two possibilities here. So it's either going to be even or odds length. But if it's even length, then the number has to be at both of these indices, like both of these even indices, in order for it to be the majority element. Because if the array is length 6, then the number has to be in here 4 times. And actually, yeah. So so if it has to be 4 times, worst case scenario, it's either at the start or the end. And so what would that look like? That would be like this, right? 5, 5. This is like the smallest amount of numbers you can have for it to be the majority element. It would have to be 4. And so when you check both middle indices, you'd get the number. And so what you could do then is you can literally just find one of these indices, then you just go left as much as you can and right as much as you can. And if it was odd, it would also have to be in the middle, right? So if an array is length 5, the number would have to be in there at least 3 times. And so worst case scenario would be like this, right? So 2, 4, 5, 5, 5. And then you can just check the middle again, and then you go left as much as you can, right as much as you can. But the problem is, while this does reduce our time complexity a little bit, it doesn't really increase it dramatically, right? So we're going to go from O of n to just starting at the start and going to the end, to O of n over 2 roughly. And if 5 is the length of the entire array, it would still be O of n, right? If just the whole array is 5, 5, 5, 5, 5, whatever, then this would still be O of n. So can we improve upon that? Can we do something better? Well, for sorted arrays, you usually do a couple things, right, that are common algorithms. You usually do some kind of left and right pointer because it's sorted, and then you can like close in on what you want. You could do that, but once again, if your number is really big, or if your number is really small, like let's say if you started the left and you went to the right, like, and that would be your thing, and you would just close in until you actually get the number on both sides. Well, if the array is length n, and then your target is n over 2, or even worse, right? Let's say you only have, let's say the target is like at, like, let's say this is 1,000, n equals 1,000. And let's say this is a false, but now your n is at index, like, whatever, 500 or something. Well, now you'd have to actually go 500 times, like, in here. And so this would still be O of n. So no matter what you do out of all these, it's not great. And so what's another thing we can do? Well, another thing we can do is a binary search. And so what this is going to look like now is we have some numbers, right? So we have 2, 4, 5, 5, 5. And what we're actually going to do is we're going to do 2 binary searches. So our first binary search is going to find the leftmost index of like the first 5. It's going to find this one. And then our second binary search is going to find the rightmost index. And so how that's going to look is we'll be at some index, and we're just going to keep trying to go left. right? So we'll have a couple cases and we're going to keep trying to go left. And the only time we won't go left is if we're like too far left, right? So like if we hit this number 4 and we're too far left, then we know, okay, we need to go right, right? And so now the way to make these indices, these left and these rights, to get the leftmost is we can technically just use the whole array, I believe, but the issue with that, yeah, so we can use the whole array, and then if we're at some number that's greater than 5, then we have to go left, and if we're at some number that's less than 5, we have to go right. And technically, we can like use half the array, but the time complexity would be the same. And so we would get the leftmost 5, we would get the rightmost 5, we'd get both of these indices, and then we can figure out how many 5s that is, right, by like right minus left type thing. And then we figure out if that's more than half the length of the array. So that's what we're going to code up here. We're going to have a binary search, and we're going to get the left and the rightmost index. I do think you can actually do like a one-pass binary search, but either way, if it's one binary search or 2, the time complexity is going to be exactly the same. So we're just going to do 2. Okay. So we're going to have a left and a right. Standard binary search. Nums -1 here. And I might even like just copy paste the code twice. You could probably make a helper function if you wanted to. You know, like a binary search helper function, but it'll be fine doing it this way. Okay, so now we're searching for the target. So we're gonna say while, and then we do want like our actual result. So let's just say that, let's call this left index, and then we're gonna make that. So we're actually gonna try to maximize that, and so by maximizing that, we are gonna want to have it be like infinity or something, right? So, or sorry, we're gonna want to minimize that, right? Because we're trying to find the leftmost index, so we're going to make it infinity, and then we're going to try to minimize it and have it be as left as possible. Okay, so while left is less than or equal to right. So now let's think of our cases. So if, well, for the first case is if our number is target, right? So if nums, oh, we do need to get a pivot, by the way. So pivot equals left plus right, on 2. So if nums pivot equals target, we're gonna try to minimize our left index here. So left index equals min. So if this value of 5 is a smaller index than we've seen previously, we're gonna update our result. So that's gonna be left index, and that's gonna be pivot. Okay. Now what we also need to do is remember, now that we check this index, we need to go left. Because like if we're at like this value 5, we want to see is there anything to the left. And so in this case, we'd say right equals pivot -1. Okay, so there's a couple other cases. So else nums pivot is greater than target. Then what would we want to do? We'd want to go left again, right? Because we're somewhere over here. So we're still going to go left, but now we're not going to update our index. And then else, so then the only other possibilities is if our index is less. And if our index is less, then we're going to want to update our left. So that's left equals pivot +1. Okay, so now we have this left index. Now we literally do the same code, and we get a right index. By the way, we can also check here. So if we never found anything, we can also just return right away here. So if left index, or we'll do it. Yeah, sure, we'll do that. We'll do that here. Fine. The left index equals float inf, meaning we never found the number. Then we just return that it's not the majority element, obviously, so false. Okay. So now we do the same thing with a few changes. So we can technically just start at the left index to get the right index, but time complexity will be the same, but let's just do that, right? Because we know that like we don't need to start at the beginning of the list, we can just start at the left index technically. Okay, so now right index. And now remember, for the right index, we're trying to minimize, or actually we're trying to, what are we trying to do? We're trying to maximize it, right? So it's going to be the rightmost value. And so we're going to make this -infinity. Okay. And this should guarantee find someone, because we know that we already found something once we have a left index. So now let's think about this. So if nums pivot equals target, remember we're trying to maximize it. So we're going to do max here. Now, if we're trying to maximize, if we did hit like a 5, we want to go to the right, not to the left this time. So this is going to be left equals pivot plus 1. Now, if our number is greater, we still have to go left, right? Like if our number is over here, then we're too far to the right, so we have to go left here. And then otherwise our number is smaller. I don't think our number can be smaller here, but we're going to leave that because we're starting at the left index. So technically our number can't really be smaller. It can only be greater or equal. So, I mean, I think if we get rid of this else, it'll still work, but I'll just leave it. Okay, yeah. So if we have a left index, we're guaranteed to have a right index, by the way. And so now we just simply get like how many, like count or whatever it is. So count equals right index minus left index plus 1, right? Same as like a sliding window or a 2-pointer. The number of elements is always the right index minus the left index plus 1. Now we just say return count is greater than length nums over 2. Okay, and that should be it. So hopefully we didn't screw anything up. Let's find out. Okay, cool. And so that's correct. So let's do the time and space here. So for time, remember we did 2 binary searches, and a binary search is n log n, where n is the length of nums. And our space, did we make anything else? I don't think so. We just used a left and a right pointer and things like that. We didn't have any new data structure, so that's going to be O1. Okay, so that's the optimal solution to this problem. Hopefully you liked it, and if you did, please like and subscribe to the channel. It helps grow it. And thanks for watching, and I'll see you in the next video. Bye.